Hey guys, it's me Sharon, and today's lesson is on the colligative properties of solutions.
Hello everyone, today we're going to talk about the colligative properties of solutions. Now, because of the presence of solutes in a solution, the properties of the solution are different to those of the pure solvent. This makes sense and it follows with our intuitive understanding of the universe as we would expect. So this word colligative means from the collection, and it has to do with the number of solute particles and not the nature of the solute particles. So we're not that concerned about what the solute particles are, it's just the fact that they're there that really matters. So there are two physical properties that we're going to discuss that are changed by the presence of solutes. It turns out there are more, but we'll discuss only these two, and the first one is freezing point depression. So let's have a look inside this solution here. We have, if you're looking down here at this solid crystal, you have here the liquid. These guys are water, but it could be liquid particles. They're trying to join the crystal and freeze. Of course, if you have solute particles in the way, as I've shown in green, they are getting in the way of the liquid particles, the solvent particles, joining the crystal and freezing. Consequently, the freezing point is depressed. It takes a lower temperature. And there's the idea the presence of solute particles interferes with the freezing process. You have to get colder for this solution with solute particles in it to freeze. And the temperature that we freeze at is decreased. And you can see here that the freezing temperature of the pure solvent and the solution are different by this thing we'll call delta TF, which is a change in the freezing temperature. Boiling point is also affected. So let's look here at a solution that's boiling. We'll put some heat underneath of it, and you can see the water molecules escaping, turning into the gas phase. Notice that because of the presence of the solute particles, again shown in green, it's harder to vaporize the solute molecules, either because they're attached to the solute particles, or perhaps they're just getting in the way. Consequently, you require a higher temperature. So the boiling temperature is increased. And again, here you see the boiling temperature of the solvent increased up to the boiling temperature solution by this thing we'll call delta Tb, or the change in the temperature of boiling. So let's consider the magnitude of these effects now. And if we have a look at the, for instance, boiling temperature, we'll say that the difference in the boiling temperature will be somehow proportional to the concentration of the solute particles and, of course, on the solvent. Some solvents this will have a great effect on, others a smaller effect. And that's relatively direct, and we could accept it pretty much right away for what we'll call non-dissociative solutes. In other words, solutes that don't come apart. One particle into the solution turns into one particle floating in the solution. Covalent solutes are typically like this. But for dissociative solutes, for example, soluble ionic compounds, we'll have to account for the fact that the formula unit of an ionic compound may be able to dissociate and break into ions and consequently have more particles dissolved in solution than were put into the solution as solids. Okay. Fortunately, we have a friend here in Jacobus Vant Hoff, and he's a very prominent chemist. He's a Dutch chemist and started his work in the world of veterinary medicine, interesting enough. He's developed this thing called the Vant Hoff ratio. By the way, he got the first Nobel Prize in chemistry, so no dummy. So his suggestion here is that the Vant Hoff ratio will be the ratio between the dissolved particles in solution and the ones you put into solution. So here we have the delta Tb, or the change in the boiling temperature, will be Kb, some factor of the solvent, times the molality of the solute particles times Vant Hoff's ratio. And delta Tf, the change in the freezing temperature, will again be a factor for the solvent Kf times the molality, curly m, times again I, the Vant Hoff ratio. Remember, delta Tf is the change in the boiling or freezing temperature. So let's have a look at this and see if we can make some sense of it. We're going to dissolve here 120 grams of sodium chloride into 500 grams of liquid water and ask what is the new freezing temperature for this solution. So we'll compute delta Tf equal Kf times molality times Vant Hoff ratio. Turns out that Kf for water is 1.86 degrees Celsius multiplied by kilogram of solvent divided by mole solid, or 1.86 degrees Celsius per molal. The sodium chloride dissociates into sodium and chloride ions. There are two of them totally, so the Vant Hoff ratio here will be 2. That is, 2 particles in solution for every 1 particle you place into solution. So here we have delta Tf equal Kf, 1.86. Here we have 120 grams of sodium chloride. Use the molar mass of sodium chloride and divide that by half a kilogram of liquid water here. Multiply by the Vant Hoff ratio. Notice the yellow here is the molality. I, the Vant Hoff ratio in blue. Check all the units, and we wind up that the change in the freezing temperature will be 15.3 degrees Celsius. That is to say, the freezing temperature of the solution is the solvent 1 minus delta TF. Remember, the freezing temperature will go down, and 0 minus 15.3 degrees Celsius is negative 15.3 degrees Celsius. So this solution will have a significantly reduced freezing temperature. Here's another example. We're going to dissolve now 125 grams of N2H2 into 0.85 kilograms of acetone and ask for the new boiling temperature of this solution. Now we're going to need the Kb for acetone, the boiling temperature elevation constant, which is 1.71 degrees Celsius kilogram per mole, and the boiling temperature for acetone pure is 56.5 degrees Celsius. Notice that I is equal to 1 here. There's a covalent compound in a non-polar solvent, so there'll be no dissociation. And here we'll just write down the expression delta T equal K times molality times Vant Hoff ratio. This is boiling, so it's delta TB, Kb times molality times I. Putting in our values of Kb and now the molality, it's 125 grams divided by 30.0 grams of N2H2 and to get the mole here, and divided by 0.85 grams of acetone and multiply here by the Vant Hoff ratio. So there we have the Kb, here we have the molality in yellow now, and finally blue we have the Vant Hoff ratio. Checking all the units, and we see that this value is 8.37 degrees. That is to say, the boiling temperature of this solution has been increased by 8.37 degrees from the 56.5 degrees it was before you put in the N2H2, and the new boiling temperature will be 64.9 degrees Celsius. So there we are for now, a simple look at the colligative properties of solutions, at least the boiling point elevation and freezing point depression. Next time we'll use these colligative properties to identify solutes, and it really does get quite interesting. So stay tuned and see you soon. Do have a look at the next 2 videos in the playlist for more, and stay tuned for our next lesson, number 28, solute determination using colligative properties.
This is my dad's YouTube channel. It's awesome. So like, comment, and subscribe!